In the previous lecture, we finished chapter 2, which is about partial derivatives. We now have chapter 3, which is about double integrals. In this chapter, we talk about double integrals for the functions of more than one variable, one independent variable. Here we have 4 sections. In the first section, we have definitions and iterated integrals. In the second section, we have double integrals in Cartesian coordinates and Fubini's theorem. Then we have double integrals in polar coordinates, and in the last section, we have applications of double integrals. We have these 4 sections. In the first section, as I said, we have definitions and iterated integrals. We say the reverse process of partial derivative is partial integration. In the previous chapter, we talked about partial derivatives, and here we have partial integration. That's integration with respect to one variable by regarding the other variable as constant. Yeah, it's the same as the previous chapter when we took the partial derivatives with respect to one of the variables. We dealt with the other variables as constants. But here we have integrations. When we take integration with respect to a variable, we let the other variables to be constants, or we deal with the other variables to be constants. For example, when we say the integration of x squared plus y dx. Here, the integration is with respect to x, because here we have dx. That means we take the integration with respect to x. So the integration of x squared is x cubed over 3. Is it? How about the integration of y? No, it's integration, it's not derivative. Let's say it's a. What's the integration of a? It's a times x. Then plus c. This is how to use or how to find the integration with respect to a variable. Okay, so what if we take the integration of the same function with respect to y? If we have x squared plus y dy, about this one, here we have dy. That means we take the integration with respect to y. X squared is a constant. Let's say it's 3. So the integration of 3 with respect to y is 3y. Is it? And here you have x squared. So x squared is a constant. Integration of a constant is the constant times the variable that you take its integration with respect to. Here it's y plus integration of y is y squared over 2. It's y squared over 2. Then plus c. This is how to take integration with respect to a variable. And here you have some examples. You have these 2 examples. For the first one, let's see if we have enough place. Yeah, we have enough space. For the first one, we say the integration of x plus 3y plus 7 dy from 0 to 2. Here we have the integration of this function with respect to y. That means x is constants. Yeah. First, we have the integration from 0 to 2 for x plus 3y plus 7 dy. It equals. Here, we first take the integration, and then we use the upper and lower limits of the integration. I mean 0 and 2. Here, the integration of x with respect to y is x times y. It's xy plus 3y if we take its integration with respect to y, is 3 over 2 y squared. And integration of 7 with respect to y, 7y, from 0 to 2. We now replace y by 2, only y, because our integration is with respect to y. That means we replace y by these two values, by these two lower and upper limits. Here it equals, first we replace y by 2, then we replace y by 0. We don't replace x by anything, because here we have the integration with respect to y. We say it equals, if we replace y by 2, we get 2x plus 6, is it? We have 2 squared is 4. 4 times 3 is 12. Dividing by 2 is 6. Plus 14. Then minus. Then we replace y by 0. So it's 0. I'm just going to write down. If you replace y by 0, this term is 0, this term is 0, and this also 0. So all terms become 0, and we get 0. It equals to 2x plus 20. This is the result for that integration. Since we take the integration with respect to y, we just replace y by lower and upper limits of the integration. For the second one, we have integration of 0 to 1 for x plus 3y plus 7 with respect to x. Here, we take the integration with respect to x. And we use the lower and upper limits of the integration for only x. It equals, so the integration of x with respect to x is x squared over 2 plus 3y, its integration with respect to x is 3yx plus 7x. So it is from 0 to 1. Now we replace x by 1, then x by 0. We don't replace y by anything, because our integration is with respect to x. It is, if we replace x by 1, we get 1 over 2, because 1 squared is 1, plus 3yx, x is 1, so you get only 3y plus 7. And if you replace x by 0, all terms become 0, and you get 0, minus 0. And it equals a half plus 7 is 15 over 2. Yeah, it is 3y plus 15 over 2. This is the result of that integration. Here, we don't add the constant for the integration because it's defined. It's defined integrals. Here, because we have lower and upper limits of the integration, that's why we don't add c as we added here for the integration. We don't add c for the integration because it's defined. Here we have no lower and upper limits. That's why we add c. It's definite integrals. This one is definite integrals, but this one is undefined integrals. That's why we add c for the integration. That's all. اگر هاتو سنوردار بو definite بو پێویست ناکات c بۆ زیاد بکەین کاڵێن بڵێن زای c لە کۆتایی integration-ەکە. Okay, but if this indefinite, we must add c. Now we have double integrals. Double integrals is so easy. If you just know how to take a single integral, double integral is c. It's so easy. It's similar to that. But you take the integration twice. It's the same as the second partial derivative. When you took second partial derivative, it's easy. It's the same as the first one. But we take the second partial derivative for the first we take only a derivative for the first derivative. And here also we do this the same. We say if R be our region to be xy, where x from A to B and y from C to D. That means here, when we take the integration with respect to x, so the lower limit in integration is A, and the upper limit in integration is B. And here, when we take integration with respect to y, the lower limit integration is C, and the upper limit integration is D. We say, and f is continuous in the rectangular region, then let me draw the rectangular region here. Let's say this is A, this is B, and this is C, this is D. So if we draw this rectangular region, we say x is from A to B. X is from A to B. From A to B. And y is from C to D. So what's the region? Is here. This is our region. This is the region of x from A to B and y from C to D. This is the region. So x is from A to B and y is from C to D. Is it? Look, this is x and that's y. Here, x is from A to B. On the rectangular region, we say x is from A to B. Horizontally, we go from A to B. And vertically, which is y, we go from C to D. And we say the area of this region, the area is the double integral of f of xy dy dx. The first integration is for y, and the second integration is for x. Okay, the first integration is for dy. Since you have dy then dx, that means the first integration is for y. We take it with respect to y, and these are the lower and upper limits of the integration. And then we take the second integration with respect to x. We use these two lower and upper limits of the integration. As you see here, it's written that first we are going to find the integration with respect to y and we find the results. Then we take another integration with respect to x. Okay, but if we have dx dy, as you see here, we have a and b, but before we had c and d. We have c y because dy, we say y is from c to d. Y is from C to D. That's why we say if we have dy, then you must have from C to D. But if we have dx first, we must have the lower and upper limits for x. X is from A to B. Then dy, we have the lower and upper limits for y. That means here, we take the integration with respect to x, then we take integration with respect to y. Now we have some examples. We say the double integration of y cosine x dx dy. Y cos x dx dy. Y here, as we have dx, that means x is from 0 to pi over 2. Let's draw the origin. This is 0, let's say this is pi over 2. and this is pi over 6. Okay, that means x is from 0 to pi over 2 and y is from 0 to pi over 6. This is our origin. This is our origin. X is from 0 to pi over 2. That means when we take the integration with respect to x, we have from 0 to pi over 2. And then when we take integration with respect to y, we have from 0 to pi over 6. Okay, let's find it. For part I, we have the double integration from 0 to pi over 6. These two values are for y. And for x, we have from 0 to pi over 2. Y cosine x dx dy. What's the first integration? Yes, it's with respect to x. So y is a constant here. The integration of cosine is sine. The integration of cosine is sine. And you get the integration from 0 to pi over 6. Then we have y sine x from 0 to pi over 2 dy. We have that. Is it clear? We first take integration with respect to x and we use lower and upper limits. Then we take integration with respect to y for the results. This is integration with respect to x. You find it first. This is the integration. Then we replace x by pi over 2 and then by 0. Okay? We say it equals integration from 0 to pi over 6 for y sine pi over 2 minus y sine 0 dy. We just used the lower and upper limits of the integration. We first replace x by the upper limit, the minus we replaced by the lower limit of the integration. Sine 0 is 0. That means y sine 0, here we get 0. But here sine pi over 2 is 1. That means we get the integration from 0 to pi over 6 for y dy. Is it? Because sine pi over 2 is 1 and sine 0, so all of this term becomes 0. But here it's 1. Y times 1 is y. That means we just get y. The integration of y cos x with respect to x for x from 0 to pi over 2 is only y. We get y dy. Now we take this integration. That's what. Taking this integration equals y squared over 2 from 0 to pi over 6. It equals pi squared over 36 times 2 is 72 minus 0, which is pi squared over 72. This is the result. This is the double integration. Okay. How? How كشيء بس أنت لو زيادة شوية irrational number أنا جماعة باكل كده. Okay. But pi is an irrational number. Is that easy? Okay. Let's take the second one. The second one we have sine x squared y dx. Sine x squared y dx. dy dx. We have the double integration sine x squared dy dx from 0 to x, then from 0 to 4. We have this. So what if it was dx dy? About this one, can we find this integration? No, because you have no derivative of the angle out of the function. Okay, we must have 2x, then we can find its integration. We cannot find this integration. Okay, but if we have dy dx, it's easy to find because this is constant when we take integration with respect to y. Is it? It's a constant. Let's find first integration with respect to y. Okay, it's given like this in the example. And let me check if there's any space. Yeah. Here we have the double integration. Let's say from 0 to 4 for the integration of sine x squared dy from 0 to x, then dx. Okay, we are gonna find this one first, then we take another integration with respect to x. First, we take integration with respect to y, then we take integration with respect to x. And this equals to what? What's the integration of sine x squared with respect to y? So, look, sine x squared is a constant. Its integration is the constant times y. Let's say it's 3. Let's say it's 3. Integration of this, it equals to what? 3y. But here we have the same. It's a constant. If we take its integration with respect to y, it is y sine x squared. We get integration from 0 to 4 for y sine x squared from 0 to x, then dx. Look, we first find this one. It's all together. We take this, then we take another integration with respect to x. And so we first replace y by x. We don't replace x by itself because we took the integration with respect to y okay, so we have the integration from 0 to 4 for what? For x sine x squared minus 0 sine x squared dx equals, this is 0 and this is itself. We get integration from 0 to 4 for x sine x squared dx. Can you find this integration now? Yes, because we can create the derivative of the angle. The derivative of the angle is 2x. So you must have 2x here. You must have 2x. And we add a half in the out. Okay? And integration of sine is minus cosine. Integration of sine is negative cosine. And it equals a half minus a half cosine x squared from 0 to 4. Now you replace x by 4, then x by 0. It equals minus a half cosine 16 minus a half cosine 0. It equals minus a half cosine 16 plus a half. This is the result. Okay.
describing the solved equation because we had d over x, dx I mean. If that dx
Okay.
y,
Okay. If we have, let's say, integration of sine, let's say x squared dx, we must have derivative of the angle. Then we can find it. How to create the derivative of the angle? Later, بهالشيء not one. Sorry. Okay. We solve these two examples, which were about double integrations. We now have some properties of double integrations. We say if f of xy and g of xy are continuous on a closed and bounded region R, then the double integration over the region R for k times f of xy dA, it equals to, here we can take this constant out of the double integration. That means if we have a constant which is multiplied by a function, we can take it out of the double integration. We have k times f of xy. We can bring it out of the integration. And here we say the double integration over the region R for f of xy minus plus g of xy dA, it equals to the double integration for the first function minus plus double integration for the second function. That means you can take the double integration for each term separately or each function separately. That's it. It equals to double integration of f of xy and double integration of g of xy over the region R. We say the double integration of a function over the region R is always greater than or equal to 0 if the function is greater than or equal to 0 in the region. If f of xy is greater than 0 over the region, then its double integration over that region is greater than 0. And the double integration of f of xy over the region R is greater than or equal to the double integration of g of xy over the region R if f of xy is greater than g of xy. Yeah, we say the double integration of f of xy is greater than the double integration of g of xy if f of xy is greater than g of xy, as it's written here. And if our region is two separated regions, for example, let's say if we have this, if you have these two regions, this and this, if these two together to be R, this is our region. Let's say this is A, let's say this is S1 and this is S2. We name this part to be S1 and that name to be S2. We say the double integration of f of xy over the region of all of the region is the same as to say the double integration over this part of the region plus the double integration over this part of the region, where the intersection of these two subregions is an empty set. That means if there is no common point between these two subregions, this and this, if there is no common between these two subregions, we can separate them and we can take the double integration for the function at each of the subregions, which are S1 and S2. Here we have a theorem says if f of xy is continuous and non-negative on a region R, then the volume of a solid lying beneath the surface and above the region R is given by this. That means if you look at the graph here, this is the region, this one. This is the region. And this black one is the surface. So the volume here, this was between, this volume was between the region and the surface, is the double integration for the function, as the double integration of the function over the region for f of xy, for f of xy. We say the volume of a solid lying beneath the surface and above the region is given by the double integration over the region for f of xy dA. And we say the area of the region is the double integration over the region. Here we have no functions. We just have one here. Let's say it's one. We just say double integration for one. As dx dy or dy dx. That will be given in the example. That's it here. It's all about the theorem. Let's take an example there about this one. Okay. Let's take an example. Find the volume of a solid which is bounded by the function f of xy, which is, let's say, x squared plus 2xy. From above, listen, you don't need to write down above, and the region and the region R to be xy, where x is from, let's say, from 1 to 2, and y from 0 to 3. We have this example. It says, find the volume of a solid which is bounded by the function f of xy, which is x squared plus 2, let's say x squared y squared, and the region R, which is from x from 1 to 2 and y from 0 to 3. And then find area of the region. This is all what we talked about here in this theorem. We can, here, we have given the function, and we also have given the limits of x and y. X is from 1 to 2, and y is from 0 to 3. Okay? For the function, we can take the integration with respect to x first or with respect to y first. Okay, any of these we could find them. Later, هل كان أول begin that تاو كارك أصلا كان أول. Okay, here we say v equals the double integration over the region R for f of xy dA. dA means it's over the region, over the area. This equals the double integration for f of xi. What's f of xy? F of xy is x squared plus 2x squared y squared. Then, which one should be first? Here, you can take x or y to be first. Let's say, because here, both are constants. X from 1 to 2 and y from 0 to 3. If y is from, let's say, x to 2, at this case, we must first take the integration with respect to y. Okay, since both lower and upper limits are constants for both x and y, we can take any of these first. Let's say dx, dy. What's x is from? X is from 1 to 2, and y is from 0 to 3. We take this integration, and that is the volume for the solid. Here we say it equals, we take the integration with respect to x, it equals the integration of 0 to 3. What's the integration of the function with respect to x? As x cubed over 3 plus y squared x cubed over 3. Is it? From 1 to 2, then dy. Yes, I forgot this too. Now we replace x by 2 first and then by 1. We get the integration from 0 to 3. For first, if you replace x by 2, we get 8 over 3 plus 2 is 16 y squared over 3. Is it? Then minus, we replace x by 1. We get 1/3 plus 2y squared over 3. Then dy. We first try to simplify this. Then we take integration with respect to y. It equals the integration from 0 to 3. The first one, it becomes, let's find the common denominator between all. The common denominator is 3. Okay, it's 16 minus 2 is 14 y squared minus 7 dy. We get that. After simplifying it, we get this. You have 8 over 3 minus 1 over 3, which is 7 over 3, and 16y squared over 3 minus 2y squared over 3, we get 14y squared over 3, and we get 14y squared over 3 minus 7 over 3, which is 14y squared minus 7 all over 3. Now we take integration with respect to y. It equals, here we get, let's separate them. It's easier to take the integration. Let's take this two out. Is it okay? Okay. Here we get 14 y cubed over 3. Here we have 1/3 also. We have 1/3 14 y cubed over 3 minus 7y from 0 to 3. Now I will replace y by 3 first, then by 0. It equals 1/3 times 14 times 27 dividing by 3 minus 7 times 3, which is 21. is it? Then minus 0. If you replace y by 0, you get 0. And you get, yeah. If we take 3 as the common, let's simplify it first, then we do. We get 1/3 multiplying by 14 times 9 minus 21. Is it? Here we cancel out these, so it becomes 9. Now, if we take, if we divide both terms by 3, we get 14 times 3 minus 7. 14 times 3 is 42. This is the volume of the solid. It's unit cubed, is it? So the unit for this result is unit cubed. If the units are meters, we say meter cubed. As in centimeters, we say centimeters cubed. So this is the result. And now we are going to find the area. It says area of the region. Area of the region is only taking the double integration over the region. That means we say area of the region is the double integration for d, let's say x dy. What's x is from? X is from 1 to 2. Y is from 0 to 3. It equals, this is 1. We have only 1 here. For finding area of the region, we say it's just taking the double integration over the region. That means we don't use the function here. We just use 1. Our function here is 1. The integration of 1 dx is x. So it's x, the integration of from 0 to 3 for x from 1 to 2 dy. And it equals integration from 0 to 3, 2 minus 1 is 2, is 1 dy. Now, we take another integration with respect to y. It is y from 0 to 3, which equals 3. Unit squared. And let's draw the graph to know that the area is this unit, 3 units. Look, we say x is from 1 to 2. If x is from 1 to 3, it's 1 to 2. X is from 1 to 2. And y is from 0 to 3. This is 1, 2, 3. That means we have these 3 units. As you see, this is a unit. This is another unit. And this is also a unit. We have 3 units, is it? And you got the same. You said 3 units, the area is 3 units. The same. You don't need to draw the graph that I draw it here. See? أما؟ لا. أيوة بس solution هيك. Impedance graph. You don't need to do the graph. It's just for satisfying it. لا أو درسناك أنا. لا أرسل أم درسناك. Look here, we say y is from 0 to 3. When we say the double integration First dx, then dy. That means this integration is for dx. That means x is from 1 to 2. ليه يكم تاو قريب من شيء x. هذا x كم نجمع شنو؟ أي دواتر y. دواتر أنا أمام بو y. Y كم لو بو. That's why we say it's from 0 to 3 because dy is the second one. Okay. Yes, it's be given, but it's not. Okay, but you should know. Here, in these type of examples, you can use dx dy or dy dx, any of these, and you get the same results. In these type of solutions, in this type of questions, if x is from a to b and y from, let's say, c to d, that means if these all are constants, you can either take dx first or dy first. In both cases, it's true. But if, let's say, if you have y, let's say from 0 to x, and x from a to b. In this case, which one should be first? Let's say c to x. Here, this should be first. I mean, we must take the first integration with respect to y. So the integration becomes dy dx. That means it's from c to x, then from a to b. Okay? Always the constants must be the second. But if both are constants, it's okay if any of these to be first and which one to be the second. Okay? Now you have Frobenius theorem in Cartesian coordinates. It says Frobenius theorem, rectangular region. We say if R to be a region, X is from A to B, and Y is from C to D, and f of xy is continuous on the region. So f of xy is always must continuous on the region. Then you can find its integration. If it's not, we cannot. Yeah, we say the double integration of the function over the region A, it equals the double integration dx dy. X from A to B, as you see, this one belongs to the first integration. And this is for the second integration. And y is from C to D. It's also equal to f of xy if we take y first and then x. Look, it's the answer for the question that you asked. We say if both are constants, these are constants, then we say the double integration of the function over the region dx dy, it equals to the double integration for the function dy dx. That means changing the order is okay, but you should be careful about the lower and upper limits. Here we have a and b for x. As you see here, a and b is here for x. It's changing. The lower and upper limits are going to be changed regarding dx and dy, regarding the order of the integration. But if we have the region, R1, we have two regions here. If we have in R1, x is from A to B, that means lower and upper limits for x are constants. But for y are functions of x. These are not constants. In this case, we must take dy first. We must take the integration with respect to y first, and then with respect to x. Okay, as you see, it's written here. It's not written equal to the integration from a to b for dx and g1 of x to g2 of x. That's not true. Okay, we must take the integration with the variable which is its lower and upper limits are not constants. ليه lower و upper كم يكون constant اثنين y كواتا بتشيب كين يكم تاو كاريما بنسبة y bits. Okay, and the second is with respect to x because it's constants. This one is for the second integration, but this one is for the first one. As you see, that's the origin. This is our origin. We have these two functions. Y is from G1 to G2, and X is from A to B. Okay. So that's this region. We are gonna find this region. We are gonna work on this region. And if R2, as you see here, in this case, X is a function of Y, and Y is from C to D. In this case, which one is first? X. We must take the first integration with respect to X, and then with respect to Y, because Y has constants for both lower and upper limits of the integration. As you see, that's it. Here we have some examples. Let's take one of the examples and let me check. Okay, it's enough for today. Okay, it is enough for today, and for tomorrow we'll be continue on these examples.